Module 5.3 Applications of Phase Field in Mechanical Engineering. Let's start with Allen-Kahn equation. And we'll be dealing with an order parameter, phi, which we can also call it phase variable, which is 0 in phase A and 1 in phase B. The total free energy, how we define it, kind of arbitrary. So let's assume the free energy has three components. One is chemical free energy, G-chem, double well potential energy. So given on the right-hand side, you can see, and the gradient of the phase variable. We can define a parameter P and Q, which is a function of this phase variable. And these functions are often defined as follows. An important concept in the double well potential is the height of the double well, and that is denoted by W and the gradient energy coefficient A, and which follows we can solve the double well potential to get W and A, and we will use them in solving the Allen-Kahn for 1D equation. So here's an implementation. So we can define a grid of 64 compression grids NX, and the interval is 10 to the minus 6, so pretty small. We have a driving force, 10 to the power 5, 5 into 10 to the power 5. Interfacial energy as 1. So this you can also determine from density functional or even DFT calculation or experiment. Interfacial thickness, which is some multiple of that grid, and interfacial mobility, which is also given as a parameter. And then we'll try to get the BAW that we defined in the previous slide, and the phase field mobility, which is kind of related to them. And we can get the DT, which is the time increments, time of the time steps. And then we can evolve them, evolve the Allen-Kahn equation based on the rate of change of the field variable, which we can get it from the equation on the right-hand side. And let's implement it, then maybe it will become more clearer. So we are doing a time evolution, and you can see the variable phi is given by the 1/2 of 1 minus tan hyperbolic 2 in and the width of the double well, and so on. So we can implement it directly here, and then we can evolve it over n steps. So you can see we are employing kind of finite difference based method, and we can get the behavior at n step equals to whatever time you want to solve for. So here is an example. So at t equals to 0, it looks like this. At t is 500 steps, the same equation was solved, and t 1000 you can see is propagating. We can also see this in 3D, and for 3D we want to use some package like PhyPy. So in PhyPy we'll try to use the simulation of additive manufacturing, dendritic pattern growth, especially useful for converting a liquid material to a solid. So there we have a phase transformation, and the rate of solidification is often assumed and experimentally found to be proportional to the undercooling rate. And under the right circumstances, the solidification front can become unstable and leading to dendritic patterns. There's another example of that we will try to solve, or maybe give it an exercise, how ice forms from water. So that is also a good phase field problem. So unlike defining each variable and so on in the previous slide, we'll use some inbuilt functions in the PhyPy, and like cell variable, diffusion term, and so on. And here, but of course, we have to define the number of grids, the grid interval, the time step, and so on. And we'll try to solve heat equations. So del T over del T, so T is being temperature, and so on, and the phase variable. And we can have some constant parameter like alpha, C, N, and we'll try to solve this equation here. So when we try to solve this and view it using an inbuilt dendritic viewer in the PhyPy, we can see that how there was a small phase here, and then it grew, and then it grew further to make the dendritic pattern. So this is a good example of showing grain growth in PhyPy. Now, For more mechanical engineering applications, let's look at the crack propagation. So we will define a crack in a system and then solve it over time to see how this crack propagates. So we will define a grid of n, x, and y with small grid spacing and the Allen-Kahn parameter, which is arbitrarily chosen as 1 here, kappa, and how many steps you want to evolve it. And we can give an initial conditions. So and we will kind of intentionally create a crack at the middle of the slab. So the initially everything is 1, and especially at the middle, which is the grid half, +5, grid half, -5, that region we will call it -1. So remember, everything is 1, but the crack is given by -1. And now we can impose this Kahn versus Hilliard order parameter and let it solve using Python. We'll be using the Laplacian as shown here, and we can define the chemical potential that we describe in the Kahn-Hilliard equation, and we'll evolve this equation over num steps. And as you can see, we are just implementing the Allen-Kahn update that we learned in the previous slides or previous modules here, and we can also have the Kahn-Hilliard update. So a good way to see how this equation spans out, we can see that the Allen-Kahn equation have at step 0, there's a crack in the middle where we have imposed -1. You can see the color bar -1 and everything is 1 here. Now, as we go over time step 50, that you can see that -1 is kind of propagating. 650, it kind of propagate over the entire slab. There's a small center here, but after 950 steps, all of the crack have been propagated. So that's a good way to simulate a crack propagation problem in phase field.